All right, so let's talk about the collective property. In your textbook, you are going to see collective properties are properties of solutions that depending on the number of dissolved solute, but not its type. In other words, it means if today you throw in 2 mole of sodium chloride versus 2 mole of glucose, it's going to have the same effect. It's actually the number of solute you throw into the solution is going to change the property of your vapor pressure, boiling point, freezing point, and osmotic pressure. Okay, it doesn't care about what other stuff you throw in. You only care about how much the species you actually throw into the water. So it's more about the numbers, but not about the species. The property of the solution is mainly determined by the property of your solvent. What we are going to understand is actually why when you throw in the solute, this full property is going to change. We want to understand how the solute particles is going to affect it. Let's start from the vapor pressure. What is vapor pressure? The vapor pressure is actually coming from the gas molecule. It hits the glass, okay, and that gives you the vapor pressure. Once you have the gas molecule inside the space of define, so the way we define the space is actually if today you put a liquid into a flask, you cork it, you have a closed system. What's going to happen is actually the liquid molecules on the surface is going to evaporate. And those evaporate gas molecules are going to hit the walls. And those motions create the overall vapor pressure. The system, which is actually this whole thing, is not at equilibrium. The molecules on the surface start going to evaporate. Okay, and it's going to actually hit the wall, create some vapor pressure on the top. And as time goes by, you will see the water level decrease a little bit. It means actually more actual water molecules actually in the gas phase. It's hitting the wall. And then if you wait long enough, it's going to reach so-called equilibrium. At the equilibrium state, you have constant water goes from the liquid to the gas phase, which is a process we call evaporation. At the same time, those gas molecules, they are not just hitting the walls, they actually collide with each other too. When they collide with each other, they condense. So when you reach equilibrium, the two processes happening at the same rate. Rate of evaporation is going to equal to rate of condensation. And then the pressure that you measure under this very specific condition is so-called the vapor pressure of this solution. How is the solute is going to affect this property? When a solution starts to evaporate, this process happens at the interface between your liquid and your gas. The evaporation occurs at the surface at any temperature. Think about this is the original solution you have. At equilibrium, we know the gas molecule can actually evaporate and condensate at the same rate. So you throw in some solute molecules. On the surface, some of the area is going to be occupied by those solute molecules. And most of the time, it doesn't evaporate. In other words, what you do is you minimize the surface molecules that can evaporate. The end result is, since you actually have much less molecule can go up, so the vapor pressure is going to decrease. Once you understand the concept, the calculation you are going to do is so-called the Raoult's law. Raoult's law is an equation you can use to estimate the vapor pressure of a solution. If your solute is in the solid form and your solvent is in the liquid form, the vapor pressure is ultimately determined by your solvent. In this equation, it says the vapor pressure of your solution is going to equal to the vapor pressure of your solvent multiply the mole fraction of your solvent. That is actually the mole fraction of your solvent, not the mole fraction of your solute. Find the vapor pressures above a solution of 1 mole of glucose dissolved in 9 mole of H2O at 25 degrees C. There's actually one more information I need to give you. Given that The vapor pressure of pure water is 23.9 torr. Once you see this keyword vapor pressures, the equation that comes to your mind should be the Raoult's law, where it says the vapor pressure of your solution is going to equal the mole fractions of your solvent multiply the vapor pressure of pure solvent. If today you have only pure water, that means your mole fraction is 1, right? You know your vapor pressure is going to equal to this value. Today, if you add in 1 mole of your solute into 9 mole of your solvent, that means right now you only have 9/10 of the solvent in terms of the mole fraction in your solution. The vapor pressure will only come from the 9/10 of your pure solvent. So if we put these things in writing, will be, we know your P solvent is 23.9, right? The mole fraction of your solvent is, you know you have 9 mole of H2O that's going to contribute to your vapor pressure. You have 1 mole of your solute, okay, and then 9 mole of your solvent. This will actually give you the mole fraction of your solvent. So once you do that calculation, then you know this vapor pressure of this specific solution is going to equals to 0.9 times 23.9. That's going to give you a value of 21.5 torr. If you plot out the vapor pressure of your solution versus the mole fractions of your solvent, you're going to see a picture like this, just a simple straight line. The x-axis, you're going to see the value change from 0 to 1. So that means this is your P naught solvent, right? How about here? Pure solute, okay? Anything in between these two ends is actually a mixture. This straight line means the vapor pressure is purely determined by the amount of solvent you have. And it also means the interaction between your solvent and solute is no interaction. Because if you have interactions, then the curve will actually look differently. If you have strong interaction between your solvent solute, or you have your solute inside your solution, it's going to attract those solvent molecules. And the net result is they make the evaporation process more difficult. Therefore, if you measure the vapor pressure of that kind of solutions, you will see it decrease compared to the ideal Raoult's law. There's actually another situation. In your textbook, they say it's actually weak solvent-solute interaction. But I really want to say if your solute and the solvent, they don't like each other. They are actually repulsive from each other. In other words, they want to kick each other out. Under this case, okay, add in this type of solute into your solution. It's going to promote the evaporation process now. Therefore, if you plot out that curve, you will be something like that line. All the things we discussed so far is actually your solute is in the solid state and your solvent in the liquid state. Things can get a little bit more complicated. If today you have your solutes in the liquid form and the solvent also in the liquid form. So how do you handle a situation like this? In our previous case, the vapor pressure purely coming from your liquid solvent. If today you throw in a liquid solute into a liquid solvent, both of them is going to contribute to the vapor pressure. Instead of using the simplest Raoult's law, the equation you need to use for this very specific question is the total vapor pressure of your solution is going to come from 2 parts. Mole fraction of your solute multiply the vapor pressures coming from your solute and the contributions from your solvent as well. A is represent your solute. B is represent your solvent. Every time we will see if you have a solute and solvent that both is in the liquid form, that means both of them is going to contribute to the vapor pressure of your solution. Then to actually use this equation to calculate the final vapor pressure. Let's do some practice. Find the total vapor pressure above a solution that contains 1 mole of ethanol and 1 mole of H2O. The vapor pressure of pure ethanol is this value. The vapor pressure of pure water is that value. Every time you see these little circles on top of some symbol, it means a pure substance. So here means pure ethanol and the pure H2O. So when you see this liquid-liquid solution and you see this keyword vapor pressure, that's the go-to equation. If today you have solid solute, liquid solvent, then the go-to equation is simply the Raoult's law. Okay, so let's do this calculation quickly. Our solute is ethanol. Our solvent is water. Trying to calculate the mole fraction of your solute. So you have 1 mole of ethanol, right? So you know the mole on the top is 1. Bottom will be the sum of your number of mole of solute and solvent, which is actually 1 plus 1. Multiply the vapor pressure of your pure ethanol. And the P naught ethanol is 44.6. Second term is number of mole of water is 1. Total number of mole is actually 1 plus 1. Then you multiply 23.9. You're going to get vapor pressure of 34.24. Previously, we only see one single curve on this fractional vapor pressure diagram. But right now, because both of your solute and solvent contribute to the final vapor pressure, apply the same concept, you're going to see 2 curves. And then the V total is the things that connects 2 dots. The next thing we're going to learn is boiling point. The boiling point is the temperature where your vapor pressure is equals to 1 atm. In order to reach 1 atm, your liquid molecules in your solution going to evaporate pretty fast. And you accumulate enough gas molecule like hitting the wall that eventually produce 1 atm of pressure. If today you add in your solute molecule into your solution, it's going to prevent the water molecule goes into the gas phase. The vapor pressure of that solution is going to become lower. In order to compensate that so that you eventually reach 1 atm of gas molecule pressure, the things you need to do is actually what? You heat harder. Once you increase the heat, then the evaporation rate is going to be accelerated. And the net result is that the boiling point of your solution is going to increase. The equation that you're going to use for this specific concept is the delta TB, which is actually the change of your boiling point, is going to equals to KB. So KB is so-called the molar boiling point elevation constant. Multiply the concentration of your solute. Remember, this concentration is a molality. You need to use the correct concentration unit to calculate the correct answer. If you use the molarity, you're going to get the wrong number. Most of the time, for these constants, you can get it from your textbook. Otherwise, the question will actually provide those constants for you. The same concept for the freezing point depression. Freezing point was defined as the temperature where your liquid molecules start to form the solid. If today you have some solute molecules that doesn't belong to your solvent, what it does is going to prevent your solvent to form those perfect crystals. They introduce many imperfect situations for your water to form the ice. And the things you do, you keep lowering down the temperature so that your water molecule moves slower and slower, so that they can actually enhance the chance they can form ice. In other words, the solute molecule is going to prevent the interaction between your water molecules. So under this situation, what we do is actually lower down the temperature further to lower down the motion of the water molecule so that they can actually form the ice. And the net result is actually if you have solute molecules get in the way, you need to go to a lower freezing point for your solution to become solid. And that's why we say the freezing point depression is going to occur when you have more solute inside your solution. Again, to calculate the change of your freezing point of your solution, the delta TF is actually change of your freezing point. It's going to equal to KF. KF again is a molar freezing point depression constant. And the M again is a molality of the solute inside your solution. With those things being said, you know how to calculate the temperature change. But in your homework, that's another thing it's going to ask you. Instead of asking you what is the temperature change, it's going to ask you what is the final boiling point and the final freezing point. Because you know once you throw in more solute, the boiling point is going to increase. So you know your final boiling point will be the normal boiling point plus your delta TB, where TB is calculated using this equation. How about your freezing point? Freezing point should be your normal freezing point minus delta TF. You need to know whether you should actually plus or minus so you can calculate the correct final freezing point and the boiling point.